Oh, wow. Yeah.
Okay, thanks for coming, everyone. So big turnout for you, Michelle.
Thanks. Well, poor students.
Not all students, plenty of staff too. So I'd like to welcome Professor Michel Destrade. He's Chair of Applied Maths in the University of Galway. And he previously was, he's an adjunct professor here in the School of Mechanical and Materials Engineering, and was previously my co-supervisor for my PhD. So there's a personal connection there. When he was a couple of years ago, a few years ago, yeah. And only last year he took a sabbatical or a career break to work at the ERC as a scientific officer. So quite a diverse background. And so we're delighted to have you here, Michel.
Thanks, Ashley. Thanks for the invitation. And thanks for coming. So who is a student? Okay. Well, I did my PhD here in UCD it was in the arts building at the time in mathematical physics. And the seminar was on 2 p.m. on Thursdays, and the professors would come and round us up to go and listen to the same, whatever it was, we had to go. And it was really, really boring at times because it was in fields that I didn't know. And so I told myself, if I ever give talks later, I will try to make them entertaining. And so you could tell me at the end if I manage or not. I will just talk about, also, yeah, it's easier as you get older and you have more and more papers and results and so on. It's easier to bring out a narrative or a story that spans, more material. When you start, you want to impress people. You just work on the one topic. You made a lot of calculations and you just put them on the screen and you lose the audience, most of the audience. And that's natural. But as you go older, like I said, you can talk about other things. I'll just talk, I guess, about one important aspect of my work over the past, I guess, 20 years. I used to work in waves in elastic solids, and then I came here in 2008 as a Marie Curie fellow. At the time, there was no age limit or no time limit, I should say, about doing Marie Curie fellowship. And I worked with Michael Gilchrist, who was the other co-supervisor of Ashling. And I had written a proposal on biomechanics. I thought, biomechanics is nice, mechanics of soft tissues. Maybe I can do those waves from hard solids into soft solids. And these are the questions I will address today. Oh, I should say, please don't hesitate to interrupt if you have any question, instead of making notes and asking them at the end, you can interrupt. And also there'll be a game at some stage. Okay, yes? Okay, can we measure soft tissue? What does that mean anyway? Measuring the properties of very soft tissues. Can we model the soft tissues? Does it have any predictive capability? Can we make sure that we don't destroy the tissue? That's important in medicine, I guess. And the last part, do we actually need models? You will see. Why would you need that? What's the starting point of all this?
Michel?
Yeah.
Are you sharing your screen?
Oh, I thought I was. Yeah. So you are screen sharing. Yes.
Oh, you are sharing.
Okay. Is that all good?
Yeah.
Okay. So I guess the main idea, if you're an engineer or biomedical engineer, is to, or even a doctor or a surgeon and so on, is to be able to figure out what's going on in the body. Maybe when you do surgery, when you're preparing for surgery, when you are studying impacts or injury or cancer growth, all those things you want to model it so that in the end, you will end up with something like this, a finite element simulation of what happens during an impact, for instance, what happens to the skull, but also what happens in the brain. And then, if you're very at depth, at finite elements, you might be able to have, in fact, here there was a zoom, you might be able to go down to the neuron and so on and so forth. Amazing scales. But really, all this precision here is as good as the model, of course, because you have to feed some material parameters. At some stage, you have to say, well, this is much stiffer than this, maybe this is much softer than that, so on and so forth. If you have low accuracy on those material parameters, then it doesn't matter how detailed your mesh is because it won't be accurate. And so you need the physical constants. So that was the starting point. How do you measure those constants? So typically, if you come from an engineering background, you will do testing in the lab. And for tissues, that's called destructive tissues, is not in situ. And what you do is you cut out a sample of tissue. So here it's, this was done downstairs here with Badar. Remember Badar? This is a sample of a pig's brain that Badar went to collect in the Bray slaughterhouse, as far as I remember. He was friends with them. They just give it to him. They just give him all those brains for free because brain matter is not in the food chain in Ireland. So he always had fresh brain. So we cut them into cuboids like this, and then here that's one type of testing, simple shear. The other types are, tension, compression, torsion. So tension and compression, it doesn't work for brain matter. In tension, the brain will just snap it will tear apart very early. In compression, it will bulge out. In shear, it works really well, and you can see that there is a really nice homogeneous deformation. And so when you do this, so that here's Badar's name, Badar Rashid, you could get pretty nice data. So here you measure the shear stress. So that's the shear force divided by the area here of contact. And you can measure that against the amount of shear, which basically tells you how far it's gone like this. And you get a nice straight line, which was, I guess, pretty unexpected, but it's very, and that's a large deformation, right? K equals 1, it means 45 degrees, just like in this picture. And then we did that for a gel as well. And then if you measure the slope here, you get what's called the shear modulus. And then we found that the shear modulus for the gel, which was really soft, was in fact 20 times stiffer than for the brain, 20 times the value for the brain. So brain matter is very, very soft. I tell you this, if you live in Ireland, you don't know that because you never see brains in the supermarket in other countries. In France, we can buy brain. In Italy, you can buy brain in the supermarket too, right? All right, Angela? You don't know? I know in France you can. And that way, it's very soft. But there you go. And that was good. I managed to get it into the Irish Times. I wrote an article about this. At the time, I was doing a secondment there. And I wrote a whole article about brain injury, 20 times softer than jelly. Okay, so that's one type of destructive testing. Another type is torsion. And this we did at UCD here with Valentina Balbi, who is doing a Marie Curie in Galway, but was seconded here with Aisling. And I think that's the machine she was using, right? Torsion is also, a common testing protocol. Typically, the machine tells you the torque, gives you the torque respect to the angle. And some advanced machines, like I guess most of them now, also give you the normal force. That's very interesting. Very interesting information because there's a phenomenon that you might not have heard of that occurs when you do torsion of a cylinder. So let's do a show of hands. What happens if I twist a cylinder, a full cylinder? I twist it, right? You get the idea here. Do you think its length will increase, its length will decrease, the length will stay the same, or you just don't know? So who goes for increasing?
Depends on the Poisson's ratio.
Depends on the Poisson's ratio, according to Saram. Who goes for decreasing? 1, 2, 3, a few. Who thinks it stays the same? Stays the same. Who doesn't know? The rest, I guess. Or in typical Irish student fashion, they don't want to take part at all. I should have done an anonymous survey. That's what I do in class now. Anyway, I want to show it to you. So we did this experiment. That's my office here in Galway. So we have a long rubber cylinder here. There's a weight at the bottom, and here's a turntable that I bought on AliExpress. And then there's a pointing finger. That's not important. But just give it some twists and see if it goes further, if this goes down, up, or stays at the same altitude. And so hopefully it works. Yes. There's even some music. What happens when you twist it? Longer, shorter, same length? So you can do this at home. You just need a rubber cord. Or stand from the physics department, turntable from AliExpress, a weight at the end with markings, and then so here oh, sorry, I should have stopped it. Okay, I'll go back. You can see that there's etchings here. At the beginning, I just go. It's just to show you. Track if the etchings go down or back. Is one that has a red mark. That's the one that's on that bar at the beginning. Red mark. Right? So now we twist. And then at the end, the red mark has gone down. But if it's gone down, it means it has lengthened. But you're right, it depends on the Poisson ratio. But for incompressible materials, there's only one Poisson ratio, 0.5, it will lengthen. That's the so-called pointing effect. A little known effect, but very interesting nonlinear elasticity problem. And it's quite easy to prove it analytically. I do that in my course for third year students in Galway. So with Valentina, we set out to see if that's what's going to happen with the brain as well. So she did those experiments, and yeah, she did measure that. Thanks to that rheometer, you can measure the normal force that the brain was pushing on the top plate. So it's pushing, it's trying to expand. There is also pointing effect for brain matter. And then with the help of Ashling, they did finite element simulations and recreated what's called, what is it here? Boxing punch conditions. So huge rotational acceleration on the brain model here, and see what happens for the shear forces, the shear stresses, or for the normal forces, the vertical stress, because there might be the pointing effect. And in fact, yeah, we found that they were both of the same order of magnitude. So it's really bad news, really, when you have a shearing or rotating motion of your brain. Not only will it shear like this, which is bad for the neurons, but also it will push vertically, even though the rotation happens in a horizontal plane. Right? And then we even did. So that's the punch of PhD students not happy with their supervisor. But you could see, we could do movies and all. Finite elements are amazing. Of course, you need the constants that we got from the torsion experiments. Okay, that's it for destructive evaluation. Any questions? So far, so good. How about a game? Guess the movie title.
American Pie.
American Pie, but there's a little twist here. What's this in mathematics? American Pie reunion, very good. Okay, what about here? We have the sum from eyes 1 to n.
Mean Girls.
Mean Girls. Excellent. What do we have here? That's harder because you need to know the movie, but it's called a dingbat, right? It's phonetics. Just say the word out loud. Half summer. There's no movie called Half Summer, but there's a movie called. No, I understand. That's good. Midsummer. Very good. Okay, and what do we have here at the bottom? The SDT, that's the speed, yeah. It's much larger than 1. The Fast and the Furious series, because there's several of them. Yeah? Okay. When I lecture, I do one test like this in the middle to wake them up. So, let's go on to non-destructive, right? You could imagine that destructive is bad news, right? If somebody wants to know what's happening in the body, you can't just take out a piece of tissue. It will lose many properties. It will lose liquid. It will be under no more stress anymore. It would be a very different from in situ. So wouldn't it be nice if we could do non-destructive testing? And we did that in the brain, so that's the brainwave, yes. We did it with colleagues in Beijing. So here you have the brain of a PhD student who volunteered. No, it's I think it's the lamb brain, but it's intact, right? So we didn't cut any sample out of it. It's a whole brain. On top of this, you have what's called the probe of an explorer. So this is an ultrasonic imaging device that gives you an ultrasonic image here. On top of this, it generates and superposes a shear wave. So that's an elastic wave that propagates inside the brain. And the ultrasonic imaging is very fast. It's 10,000 frames per second. So it can capture the wave traveling and tell you the speed. And that's what it does here. The color, the increasing, the redder it is, the faster the speed is in that point, at that point. And then the other thing we did is that we compressed the brain where we just pushed like this. And so we were able to track the speed of the shear wave with the compression. And typically that's what you have here, right? Lambda, that's the stretch ratio. So lambda is 1, no compression. And then 0.9 means 10% compression, 20%, 70%. And as you compress more and more, the speed will increase more and more. These are the data points. And that kind of makes sense, right? If you compress something, it becomes stiffer in a way. But I guess it's not obvious, but that's what happened anyway. And then you could fit those measurements to a model. So in this case, that's the so-called full model. But whatever it is that you want, you could just do now a curve fitting to evaluate those quantities. Mu and B, these are the physical constants that we're always looking for when we try to do those simulations using this model. Of course, you could also fit it to a different model if you think the brain behaves according to a different model and so on and so forth. So this is all model dependent, but the advantage now is that we don't need to destroy the brain. Of course, you need to access the brain, so that's one limitation of this technique, because the ultrasonic waves won't go through the skull. So they've done those measurements also on humans, but it was either during tumor surgery where they do what's it called, cranioscopy, trepanation, and then they have access to the brain. Or they also have done it on infants, because when you're born, for the first 6 months, the two plates here are not joined. You have what's called the fontanelle. And so they just scalped there and they were able to make measurements. Some people in France and in London. Amazing. We did those experiments on mozzarella, cooked egg white, human brain. So you guess the trend here is brain is very soft. It's softer than cooked egg brain and mozzarella. And then veal brain is a bit softer. It seems to be a bit lower. This is work with Melanie, my first PhD student, and Karin. They're based in Lyon. And they have access to humans, which is always a plus. Okay, so that was it for non-destructive testing when you want to evaluate the material constants that you will later plug into finite element simulation. But sometimes you're not interested in the model. You just want to measure the stress. Imagine, for instance, Ashley, you're interested in measuring the tension in the skin, right? That could be important because maybe you've done a graft and you want to monitor the tension because, you know, if it's a bit slack, then there might be necrosis in parts, or if it's too tense, there might be tearing of the graft. That could be important. Maybe if you're monitoring aneurysm, you want to know if it's close to the elastic limit, for instance. It might burst soon, or maybe it's very stable and it's far from the elastic limit. You know, it could be interesting to measure the stress without worrying about the material properties. And it turns out we can. So, so first, okay, sorry. A little detour now talking about skin. So this is work with Aisling. Antonia was Aisling's PhD student. And then Matt was also a PhD student, and Michael was in mathematics. We did lots of experiments on lots of volunteers. So they were live volunteers. Maybe were they in UCD? I don't know, students, all sorts. Oh yeah, it went all the way to 70, even 80. Yeah, so at the bottom here is the age, and vertically is the eccentricity of this ellipse here. So I'll show you this ellipse is, if you want a measurement of the speed at a given spot, I think it was here on the over part of the arm, with the angle. So we had a device called the viscometer. It doesn't exist anymore. I think we had one of the last ones that tells that just the way it works is very simple. It just hits the skin, and then I think it's 2 centimeters later, or is it 2 millimeters? I can't remember. 2 millimeters, 2 millimeters. Yeah, the two probes are very close. 2 millimeters further, there's a probe that picks up the signal, right? If you hit a plate like this, there's a signal that travels through the plate, and if you have a sensor at the end, you can pick up the signal. It tells you, just gives you that the time it took to reach that point. So if you do this in black here, I think yes, the natural at-rest configuration, you will find that the speed is not the same in every direction. So that points to what's called anisotropy. And that's because in the body, you have tension everywhere, or compression or whatever, but in the skin, you have tension mostly. These are called the lines of tension, and you can see that it's oriented. And another way of having anisotropy in the skin as well is because of fibers, right? There's collagen fibers that are oriented, and you know, a wave will travel faster along a stiff fiber than across it. So we did it at rest, and I think that's what it's measuring here. So it's a bit noisy, but you can see the trend that the older you are, the more anisotropic your skin becomes. Interesting. And then another thing we were looking at is what happens if you stretch the skin. So that's the red ellipse here. When you stretch the skin, the orientation of the ellipse is still the same, right? The minor and major axes are still the same, but it becomes faster in one direction and slower in the other direction. So I guess you are doing what's called strain-induced anisotropy. You are increasing the anisotropy. And then another work we did with Aisling and was the same people, was using machine learning to infer the material properties from the speeds. So when you hit the surface like this, there's what's called a supersonic shear wave front. So that's a wave that travels really fast and dies out very quickly, but it's picked up often, at least in the simulation, we see it. And I think, yeah, you can also pick it up with laser imaging. And then what follows then is what's called the Rayleigh wave, basically a surface wave, a seismic wave. That's how Rayleigh came up with them. So what Matt did and Aisling is that they ran thousands, was it thousands or hundreds of simulations with different parameters, different material parameters, and then trained machine learning process to infer to do the inverse analysis, if you want. If we give just the speed of those two waves, which is something we can measure, if we give that to the model, it will be able to predict the stress, right? So this is the stress that we know from the finite, we just impose it in the finite element simulations. And then this is the stress predicted by the machine learning protocol. Pretty good. And also it can predict the stretch. That's nice. Okay. Now, I've been talking about surface wave. Another type of wave that you might have come across is the so-called Lamb waves. Surface waves are the waves, Rayleigh waves are the waves propagating at the surface of a semi-infinite, very deep half space. Lamb wave is when the medium is thin, in the sense that, you know, the thickness is comparable to the wavelength of the material of the wave. So they are called Lamb waves. They are harder to model, and there's a lot more information to get from them, but they're very, very informative, right? So that's why I was telling you. Lamb wave, there are two types of Lamb waves, the symmetric one and the antisymmetric one. You could see that either they go like this or they go like that. That's the idea. Again, all this is very well known in acoustics. All we did was to translate that to pre-stressed materials and then find funny connections. What you will find is that there are a lot of, I guess, an infinity of waves that are generated, each of them with different frequency. So that's called dispersion. The wave speed will depend on the frequency. For each frequency, there's a different wave speed. And then when you do the analysis, you will see that rho v squared, so rho is the density, v is the speed of the wave, of one of those waves. It depends on the frequency and on those two quantities, alpha and gamma. So this is the only math part in this talk. Let's see. We have alpha depends on sigma 1 minus sigma 2. So that's the sigma 1 is this stress here, and sigma 2 is the out of plane stress. Okay, so it depends on the stress difference, or if you just have a uniaxial stress, tension or compression, it's just sigma 1. And then it depends on lambda 1 and lambda 2. So lambda 1 is going to be the stretch in this direction, and lambda 2. Okay, and alpha and gamma is almost similar, except that's the difference here. So if you look at them, what will happen is that you will have a dispersion curve. You will have rho v squares in terms of frequency. And from this dispersion curve, experimental dispersion curve, you can deduce, you can compute, you can measure alpha and gamma. And if you have alpha and gamma, it's good news, because look, if I do alpha minus gamma, yes, the fractions will disappear. I will have access directly to sigma 1 minus, or just sigma 1 if it's uniaxial. And if you do one over the other, the fractions also disappear. You'll have access to the stretch. And that's independent of the material model. It's independent of W, the strain energy. It's always true. And so I thought, isn't that amazing? I can measure the stress, or I can measure the stretch without worrying about what the material is made of. And so I turned to my colleagues who could do the simulations and who could do the experiments. So the experiments are tricky we were using what's called optical coherence tomography. That's a very advanced optical technique that allows you to see through transparent materials at the nanoscale. It's just extremely precise. And what we did, so we have this plate, we stretch it, we can measure the stretch, we can measure the stress as well, because we know how much weight we put at the end here. And then we have a piezoelectric probe here that's just going to hit the plate and generate those waves. And then the OCT system is going to just record the wave traveling. Amazing. So these are actual measures. Everything is in this slide here. So first we did it with a rubber membrane, a transparent rubber membrane, right? So it's about, that bar here is 1 millimeter. So it was about 0.5 millimeter thick. And these are actual photographs, right? We just blew up the vertical displacement because it's in the nanometer, but this is in millimeters. And you could see what happens when you hit the membrane. You see the wavefront developing in circles when it's unstretched, and then in ellipses when it's stretched. And then you do a very advanced inverse Fourier analysis here, but you can end up with this data here. Oh, sorry, here that's the photograph, the photo seen from above. You end up with the dispersion curve. You have the speed against the frequency for different levels of stresses. And then from this one curve, I can get alpha and gamma. And so from this one curve, I can get access to the stress or the stretch. And then vertically is the one we measured because we know how much weight we've put, or we know how much we stretch it. You know, we just measure the final length divided by the original length. And then you can see that the data is pretty close to what we wanted. And so we have a way of measuring the stress and the stretch without wondering what is the shear modulus, what is the, I don't know, the D constant, the third order elasticity constant, and all this. Direct measurement. And here for good measure, we did, since we have stress and stretch, we could do a stress stretch curve. Which one is it? Yeah, the real one. Just like that, we can recreate it. And then we superposed it against a tensile test, where the one that's destructive. And it's also pretty good. I was amazed by this. And so I talked to my wife about it. She said, oh, that makes me think about the bodhrán. Have you heard about the bodhrán? Do you know this word here? Yes, it's a traditional Irish drum. And here I had the YouTube video, but it doesn't work anymore. But you get the idea, right? The player used this drum here, this stick here to make it create sounds. But yeah, my wife told me, did you know, because I was telling her about hitting a membrane, she said, did you know that the bodhrán players, they sometimes wet the bodhrán because they think it's too stiff, or they dry it with a cloth because they think it's too soft, and they tune it like this. Or maybe, you know, it might evolve during the session. And so I thought, this is genius. And that's something I always encourage you to do when you do research, is think of something that's practical and that will appeal to people. I'll show you why soon. But so what I did is, so the measures were made in Boston and at Harvard School of Medicine. So I bought online, I bought a bodhrán, I had it delivered there, and they made those. So here, well, it's hard to see here, but here's the probe. And then they did the exact same as they did earlier for the rubber membrane. And so the difference between dry and damp, and so on and so forth. It's amazing. We can measure it, even though we don't know what it's, well, it's made of goat skin, but we don't know exactly what the properties are. And then when you get that, you get on the front page of the Irish Times. He's my long-suffering wife. We had to go in November, it was really cold. We had to go in the Bay of Galway to pose for this. I look like an idiot because I don't know how to play the bodhrán. But whatever. I thought I was on top of the world. After that, it doesn't get any better. It's all downhill from that. Okay, so we also did it for cling film. So here, just to show that it works for, so here that's in the micrometers, right? 10 micrometers, 13 micrometers. Those formulas I had, they work for incompressible materials, but we said, okay, let's do it for cling film, which is compressible. So we were like far off the modeling, but still it gave us a good measure of the stress, even though it's normal. I don't know. I find that fascinating that we're able to measure stress without knowing what the material is made of. And so we went on with other colleagues in Beijing now. We went on to do it for bulk tissues. So if you look into the literature, Maurice Biot, he was a Belgian, American-based, a Belgian researcher. He's known for poroelasticity, but he also worked on waves, elastic waves. He came up with this formula. If you have not this, it's not a plate, right? Just imagine an infinite or very large sample. If you're able to measure those two waves, so there's a stress applied, sigma 1, you could generate a shear wave that travels along the one direction and is polarized along the two direction, or you could go the other way, one that travels along the two direction is polarized along the one direction. Okay. The problem is, how do you do that? Right? The first one you can, you just put it on top and then let it travel. But the other one you can't, because you have to be inside the material. So just think of this as, say, a railway. You want to measure how much stress is in the railway. You could do those 2-1 measurements, but you can't do the 1-2 measurements, right? So in classical ultrasound evaluation, you will see that this formula, this 2-1 wave is easy to measure, and then they try to, connect it to the material constants, so on and so forth. But then, remember earlier I was telling you about the Explorer, that machine here that generates the ultrasound field and then generates a shear wave. This shear wave is the 1-2 wave, right? Shear wave elastomer. So we're nearly there. We just need to combine this and this, and that's what they did in Tsinghua University. They programmed the machine to not only generate this 1-2 wave, but also generate the 2-1 wave. So here's the finite element simulation, here's the measurements. And so that's great, because we have simultaneously those two speeds, and so simultaneously we can compute the stress. We can measure the stress directly without, again, knowing what the material is made of. And then they say, you know what, how about muscle, for instance? What's the difference between muscle and, say, rubber? That muscle has fibers, right? I was telling you about that anisotropy. So then that's where I had to do the mathematics and show that the formula was still working, provided you apply the stress along the fiber direction. It still works. And then we did this. And again, the wave speed, the stress that you measure this way is close to the one that you apply. Again, another way of measuring the stress directly without knowing the material properties of the muscle. So here, that's a pig. That's not a master student volunteer. Wow. Okay, and so Yang-Ping Cao and then Guiyang Li, they deposited a patent for this.
Yes.
Yeah.
I'm just wondering, I don't know much about waves. So you said along with the action on the fiber, the wave would travel faster.
Yes.
Let's say if the fibers are.
Well, it depends which wave. Yeah.
Let's say if the fibers are oriented in such a way, can that V12 square minus V21 square be negative?
Right. I don't know.
I was just wondering, because most of the measurements here, which I see.
I guess it depends on the values of the stress. But this works. This formula works.
This formula works, assuming that there's no anisotropy, right? But because of the anisotropy,
It works also in anisotropic solids. Yes, it still works. I guess all sorts of things could happen, but then, yeah, you just can't guess which speed is going to be faster than the other. You just can't guess. You have to look into the formulas. It's not obvious. It depends on the stress, depends on the stretch, it depends on the orientation and the polarization. But the formula works. Are you saying, can we get negative speeds?
No, speeds will fall positive. We're just looking at the stress values. The difference could be negative.
The difference could be negative. I guess it will happen if the difference between sigma 1 and sigma 2 is negative. Yeah. Good question. Thank you. Okay, we're nearly there. Here are my take-home messages. Soft tissues are difficult to test, and you will know that if you've tried. Yeah, they're never the same. That's the problem. My primary degree was in physics. It was great. Yeah, you go in the lab the whole afternoon, you do 20, 100 measurements, doesn't matter. We'll all still be on that nice line. If you do that for soft tissues, you come back the next day, is a different tissue. Or in fact, if you take a measurement on a different person at different age, different location, everything changes. That's very frustrating. Then here's some deep summary, I guess, experiments, models, and simulation. Okay, now wave methods, that's good. I encourage you to do that. There's not many non-destructive protocols. The other one is indentation, I guess, vibration, things like this. And then that's my discovery. That's the one that I got the front page of the Irish Times because I was talking about the bodhrán, of course. Okay, thank you very much. That's it. And that my daughters told me to use that slide, that photograph, 10 years ago. Mohammed.
Thanks. So with the membrane, with your non-destructive model, you have a membrane. So
yes.
The stiffness of the membrane depends upon tension. Right. So now as you change the tension, you increase the tension more stable. So for with membrane, how you are calculating your problems with your approach? Because I can see that this wave and land wave, that's fine, but like how the boundary conditions are affecting.
Yeah, I could do that. I could compute the material properties. I could do that. Remember that curve fitting I was showing you? By changing the stress, I can track the change in the speed. And then if I take a model, if I take a W strain energy density, I can find the relationship between the speed and the model. And then with curve fitting, I can find the parameter. But that wasn't my idea. My idea was to just forget about all this. Just measure the stress directly or the stretch.
And the damping part was interesting because some materials
yes, that's true.
And the dispersion curve for that, I can see that it's turning lower.
You can also include the viscoelasticity. Yeah, there are other. My collaborators have worked on that, and they showed that the formula was also robust, even if there was damping. So you could still link the speed to the stress without worrying too much about viscoelasticity or the model for the material.
I'm just wondering, so formula is so robust.
Yes,
it looks like
it's very robust.
where is all the physics related to viscoelasticity or anisotropy dying down? Like, why is it not contributing? Is it not contributing to the difference? Like,
yes.
Individual stresses, but is it?
Yeah, like I said, it's robust, but there are some conditions now. You have to make sure what I call right alignment. You have to make sure that the stress tensor and the anisotropy tensor are coaxial. In that case, it works. Otherwise, it's a big fat mess. Yeah. So it's robust under certain conditions, or I guess it depends how you model viscoelasticity as well. I think Harold did it with even fractional viscoelasticity and it worked. You can still ignore it. And then other people have done included viscoelasticity in the finite element simulations, and so that it didn't make much difference. Well, it doesn't affect the speed that much. It's just the propagation length that changes. Yes. I haven't tried that. I guess it works locally. I know, yeah, I think Yang Pintao and Go Yongli, they did experiments in functionally graded material. But I don't know if they tried that formula. Yeah, sure, you try it. Yes,
I'm fascinated by your picture of the radio wave, the supersonic.
Yes.
How do we get the supersonic? Is that
Yeah, it's called leaky waves. That it just doesn't travel far. The amplitude dies out very quickly, but the scale there is tiny. Like in those experiments I was telling you, 2 millimeters. You could still, I guess, you could still pick it up. I can't remember. Ashley, do you remember how far I was for the simulations?
The millimeters, like 5 millimeters maybe, and the magnitude at that point is about 400 of the amplitude of the
The radio wave travels really far. It's in fact, yeah, it can go around the Earth 2 or 3 times. Yeah, but the supersonic shear just disappears quickly. It's hard to model. There is activity on it, but it's hard to find formulas for it.
You pick it up experimentally as well.
Yeah, you pick it up experimentally, numerically. The modeling is much harder. I think you have to do complex analysis to find the roots and things like that. I'm not completely versed in that. But yeah, it does exist. But sorry, I never pay attention to that.
Are you able to extend this to do viscoelastic effects as well, or is it? Do you need to do another experiment?
Oh, there is always viscoelasticity in the experiment. But yeah, like I was saying earlier, the formula still works when it's viscoelastic. What happens with viscoelasticity is that it makes the amplitude die down, but it doesn't affect the speed much, not too much. So it doesn't slow it down. So the formula still works. It's nice.
And you double focus time as well as one way of using shoot waves in tissue.
Yes.
Solid. Can you apply them as long as you're measuring the shear wave regardless of the method you can apply the same equations, so you can do measure them.
Yes. It's tricky. The shear wave elastography is very clever. The way they do it, I guess I can show it on this image here. The way it works is that it focuses a sound beam inside the tissue, and that sound beam creates a small explosion in a way. And so if you just add the one explosion, then you will have a spherical wave. But what it does then is that it's programming that focal point to move down inside the tissue. So you have those multiple spherical, maybe you can see, no, I don't have a picture for this, spherical wavefronts that add up to make a plane wavefront. So it's going down like this, and the shear wave is propagating like that. It's very clever. With the MRI, I don't know how you could create those. Yeah, just think of, say, like a boat on a lake, and the shear wave is just the wake behind the boat. So you need to be able to create those focal acoustic beams traveling inside the tissue. With an MRI, there are other ways, I guess. There are other ways where they just put a vibrator here or a shear yeah, they shear the plate, and that generates waves. What's very interesting is that you have 10,000 frames per second, and so you can see the wave travel slowly, about 1 or 2 or 3 meters per second, but still you need to be able to pick it up. With the MRI, the acquisition time won't allow you to see the wave. So what they do then, they do, I guess, vibration techniques and sync the acquisition time to the vibration frequency and things like that. It's trickier. Ultrasound is amazing, and it's very detailed. And then optical coherence tomography is even more detailed. Or I was talking with Mohammed about laser beams on the surface. They can pick up a wave traveling with laser beam. What's it called, the technique?
Laser Doppler.
Laser Doppler, yes. So, but you are restricted to the surface, you can't see inside. With this, you could see inside. But you can't see through bones, so I don't know if you could access the heart, for instance. Things like that. Every technique has advantages and limitations, but fascinating. Okay. Maybe no question online. Forgot to ask the online people
Oh, yeah.
that question.
Anyone have a question online? You covered it all, maybe.
No,
thanks.
Okay, thank you.
Thanks very much, everyone. Michelle is here visiting me for today and for part of tomorrow as well. If anyone has questions you want to ask them, I'm sure he'll be able to.
Or about the ERC as well.
Or, okay.
Or in fact, postdoctoral funding in general. Yeah. Marie Curie as well, yes. Yeah.
All right.
Thank you.
Thanks again, Michelle.
Bye-bye.
Meeting now.
You have to go.
And I think it's free. We're going to 4:35. Are you hitting something?
No, I think